Okay, thank you. So while Surinder is setting up, welcome everybody to this session. Let's get your other friends in. It's a good day. And as I mentioned that we have a number of events scheduled for today. Besides the exciting talks by Surinder and by Shivam, right? We'll have the supercomputing facility visit, 1:30 to 2. We will have a career session and sort of open-ended ask me anything session, right, during the tutorial 4 to 5:30. And we will have a banquet dinner. That's right on the first floor up here. So please, all of you, please join us for that, for all three, for everything. Okay. So for today's talk, the first talk, we are very excited to have Surinder, who's currently the senior principal data scientist, as well as senior director at Flipkart, leading the various data science teams. He'll tell you more about that, of course. And before that, he has been leading the sponsored search machine learning platforms for two of the major search engines in industry, both Bing at Microsoft as well as for Yahoo. Right, the Panama effort for Yahoo, he's been leading that, and we're very excited. He's going to tell us about machine learning from the engineering point of view, right, and what all goes to create a machine learning pipeline. Over to you.
Right, thank you, Professor Anirban. Good morning, everyone. You got my name. My name is Surinder. Let me tell you a bit more about what I have been doing in my career. I'm at Flipkart for 7 years now, and I've seen multiple applications, multiple problems which span advertisement, recommender systems, user-generated content, which we call shortly UGC, personalization, right, user retention, and nowadays I'm leading search and couple of other business units, which we internally call BUs. Today I'm going to talk about how we apply machine learning in industry. What are the best practices? Hopefully we'll go through some of the case studies also, and I hope that you will be able to relate with them how your basics are connected with these applications, right? And in my opinion, it's pretty straightforward as long as you keep your basics grounded. I also have Shivam, who's gonna talk later, and he'll talk about a couple of sessions. A very brief overview about what we're going to cover here, right? Very quickly. How you start from given a problem, right? In industry, when you're trying to solve a business problem, what are different phases? I mean, as a machine learning scientist, as a data scientist, what are things that you go through? Right? What are the things that you have to take care of? How do you formulate your problem? I mean, business gives you one problem, and then you, as applied data scientists or data scientists, you will have to map that problem into a data science problem, right? You have learned about supervised learning, unsupervised learning, and so on and so forth. But how does that problem translate into some of those? Right? That's one. Then we'll go into figuring out, do you have the data? I mean, that's the next phase. I mean, like I said, there are different phases. Okay. One of the phases is that, do you have the data? I mean, today we have given this name, data sciences. So data is foremost over there. There is no science without data. So we'll talk about that. Okay. And so I won't actually give you the, right now I won't give you the complete rundown, but we're going to talk about different phases. All the way until deployment of the models, model development, deployment, and the steps after that. Okay. And then we'll go into deep dives. We'll take lots of case studies. One running case study, how you approach the same problem in multiple ways. Okay. So those case studies will be there, and then what will be the factors in real life, in practice, when you're working industry, when you're working at scale, what are the challenges that face you, and how they impact your modeling choices. So we'll go into those details as well, right, along with some other case studies. Shivam is going to talk about deployment and beyond, monitoring and everything. Okay. When you take your models to production, right? When you deploy your models, do you deploy all of them straight away, or do you slowly deploy? You expose some users, get the feedback, right? And in the end, I have a couple of demonstrations. One problem from end to end from Flipkart, a platform called Opus, which is online learning. Okay, and we'll see how you start from the beginning till the end deployment and what's the entire cycle. And a couple of frameworks. We have one of the frameworks for development in system in Flipkart that's called Molecule. Okay. Although Professor Nirban gave me a rundown, but I just want to see a kind of please raise your hands. How many of you have done machine learning course, basic machine learning course? Okay. And what's the breakup of students here? Like, I mean, second year, third year, final year, masters. Second year, how many of you are there? And here, third year. Okay, third year. Okay. And final year, masters. Great. And I'll assume there are some PhDs as well. Okay, I'll try to keep it interactive. Feel free to ask any questions at any point in time if you want any clarifications. Right? I might assume some things, but that would be a mistake on my part if I made that assumption and you're not aware of it. So please feel free to interrupt me and ask those questions. Yeah? Okay, then let's get started. Okay, I'll start with the. Are you aware of the term SDLC? Right, that's the traditional. How do you develop a software and what is the life cycle of a software? Now we have defined data sciences has been a field actually which has come into software. It's a recent phenomenon. I mean, it's not as mature as your standard software development life cycles. People have transitioned into roles of data sciences who are focusing completely on the data sciences, right? So this process is evolving, right? And subsequently at Flipkart here and in many other companies, we have seen that it has taken a shape of its own. The process has taken a shape of its own, and we now call it a DSSDLC, data sciences SDLC. And it's a process that helps you basically define, design, experiment, and deploy the solutions into a production setting, right? And why do we need it? First is that the execution becomes very smooth. Any project that you take, right? It's a smoother execution of that. But more importantly, people are investing their energies in the right places. It's efficient. The productivity of all the folks involved in the development of a data science project, right? That goes up. You know the roles and responsibilities. Now, data science is the development of a software is not very different from writing a paper. Since you have taken machine learning courses, how many of you have read some papers on machine learning? Okay. Then I'll assume that not many have written as well, given the low frequency. A research paper, typically, a very small laydown. When you write a paper, right, or when you see a paper, it's broken down into very couple of sections, a few segments. You start with the motivation of the problem, introduction to the problem, right? What is the problem that you are trying to solve? Okay. After that, you also, when you're solving that particular problem, you also want to see what has happened before you have tackled this problem. How have others in the field, in the academia or in research or in industry, how have they approached this particular problem? Okay. What is their work like? Can you use them? And how is your work different from them? Or how do you apply? Okay. That leads to development of your approach. Once you have looked at all the work before you, right, in that particular area, you refine, you distill your approach, your solution. Okay. And when you develop your solution, we have to quantitatively evaluate that solution, the efficacy of that solution. Okay. So that leads to an evaluation section in the paper. And it's no different in the industry. You have to do all those steps. Few other things that you have to do in production is in industry is that you have to now deploy that particular solution. It has to see the test of real users, right? The real consumers who will use that solution. Now, when you do that, you can develop a very sophisticated algorithm, right? A solution. But let's say if, when you deploy that solution and people are actually using it, can it face that amount of traffic? Can it scale? There will be concurrent users. For example, in Flipkart, we will have in thousands and tens of thousands queries per second, so what we call QPS. Okay. Now, when you deploy a solution, will it be able to stand the test of time and that much traffic? So these are the things that you have to be very, very aware of when you're deploying a solution. You can't sit in isolation and develop a solution and say, I am done. You have to work with your partners, and afterwards, once you've deployed your solution, you have to monitor maintenance. As my CDS says, a machine learning project, right? It's like a baby, it's like a living organism. You have to take care of it, which means you have to continuously feed it, you have to look after it, which means you have to monitor it, right? And if the model goes wrong, if it's not working as per your expectations, then you have to diagnose what's ailing it. This I've already covered now. When you are developing, these are dry things, so just bear with me. Few things, interesting things will come along the way. Okay. So when you are developing a machine learning project, right? We said that you have to think in terms of what is the business application, what does the business want, right? In industry, when I say business, I mean the product team or the business team, right? And then how do you apply it? How do you translate into your problem? And that's where the modeling comes. Evaluation is equally critical. Like I said, you have to evaluate what business asked and what you developed. Are they in line? I mean, they're asking for moon and you developed something else, and then you're evaluating in your own silo and say that, voila, I've got a model out there for you. Please take it. But they were expecting something else, and you gave something else. So all of these have to be in conjunction. The evaluation has to see and pass the test of the business metrics, right? And then all of these things are enabled by the infrastructure, right? The engineering infrastructure. And this is just a small thing, but this is the harsh reality of life, right? When you develop a machine learning project, we have seen data scientists develop solutions, and they will be there for waiting for months to get deployed. The infra would not be in place, right? And you will wonder what is it in my model or in my solution, right? That it is not able to go to production. And there are many areas, there are many places, right, which will result into your model sitting and warming the chairs over there. This is a slide I just came up with. I thought that I'll just give you a brief overview of things. Okay. When you evaluate, one of the core things in any machine learning project is, how do you evaluate your model? How do you measure? What are the metrics that you should worry about, right? So there are a couple of metrics. You just need to understand this chart, right? The definition of what is a true positive, what is a positive, what's a false positive. These are very intuitive, but then these ratios you just have to keep at the back of your mind when you're evaluating any model, right? So just feel free to read through it, and I'll give an example of one of the metrics, or rather a couple of metrics. One of them is ROC. This stands for receiving operator characteristics. It's a graph between a true positive rate and a false positive rate, right? It's very important. Here you are seeing, I deliberately actually put a picture which is jagged, but when you see your solutions, when you evaluate models, you will see it's a smoother curve. And the reason for that is that each point on this curve is actually a threshold. So your model has given an output. Let's say you are developing a logistic regression, okay? And you have on your data set, you have endpoints. For all those endpoints, you have a model score. Now you choose different thresholds, okay? And then you compute above that threshold. You will say, okay, if my point has a score above a particular threshold, it will be deemed as a positive, and below it will be deemed as negative. And subsequently, you come up with at each threshold, you will come up with true positive rate and false positive rate. So this is one of the most important metrics that industry measures. And the metric here is the area under this curve, okay, at different thresholds. It's It's used for comparing multiple classifiers. And the beauty about this thing is that as long as you have a monotonic function, when you rank your content, right? When the scores, any score that you have is monotonic in nature, that anything above it will be two scores when you compare, right? One score is greater than that. If you have that relationship, right? It doesn't need to be a classifier. That's all we are trying to say. So we have seen, when I joined Flipkart in the first place, and the first problem that we were, I was trying to solve over there was that of, in the ads domain, it was ad clicks prediction. And before me, someone had developed a heuristic solution. Okay. Now, they assigned manually crafted weights, something of that sort. And they said, okay, when I show an ad, this is the probability of a click, or this is the clickability. They were ranking the content, the ads in that particular manner. Okay. It was no classifier at all. They were simply assigning a score. But all you knew there was that if the score is higher, it will show up on the top. Okay. And that helped me actually. In that case, when I developed a model, I could compare my model against that. And these are the things that we have to be aware of. Does there exist a baseline? Does there exist a metric that you can compare? Can you compare two models, or rather two solutions? One could be a model, the other could be a heuristic solution. This is one of the most cross entropy or log loss. It's one of the most common losses that you will see in classification problems. Right? It's related to KL divergence, but not going in there. Right? You can think of this PX as the true class distribution, and QX as your as the distribution that is predicted by your model. Also, one of the important metrics, when you have a ranked list, when I'm showing you content, when you see web results on a search engine like Google or Bing on web, you see results, which is a ranked list of results, right? How do you evaluate that result set? There could be two results which are equally relevant. But a result which is shown, a relevant result which is shown on top position versus a result that is shown on the bottom position, right? Let's say there is only one relevant result out of 10. They are not equal, right? So you have to take into consideration the position at which the result is shown. So DCG is that, first is that it's the cumulative, it's not DCG actually, it's mistaken, I've mistyped it here. It's cumulative gain here that I've written. DCG component is that you divide it by position. You bring in the discounting factor by position, and that is critical. Okay. The metric that we use typically is NDCG, okay, which is given that when I show that result to a labeler, to a human judge, and that person labeled it for me, then I knew that what was the right order of the documents, of the items or the products that I showed on that page. Okay, now let's come back to, these are different phases of the software development life cycle. Okay. The first three phases are very tightly coupled to each other. You don't have to transition from phase 2 to phase 3 directly. You can work on them simultaneously, right? These first three phases are the phases where you figure out a problem. You have been given a business problem. You formulate it, you try to understand as much as possible, then you try to translate into one of your DS solutions, right? Or one of your algorithms, if you will. How do you translate? Is it a supervised learning problem? Do you have the labels, right? So you check the feasibility of the data. Is the data available? What kind of data would you need? Do you need features? And once you have got the features, if that is logged, and if it is not logged, you raise a request for that before even you get started on a problem, you have the requisite data. And then is the problem feasible? If someone is asking you to build something and then they tell you that no pressure, take your time, but you have 1 millisecond to serve the request, right? Then you know that outright this is not going to work out. And your solution will change. Maybe you will have a solution. Maybe you'll develop a solution which was developed offline, and in the online path, when users are actually hitting your servers, right? At that point in time, you will do a simple lookup. Maybe it will work, right? So maybe you will have that. So that's the feasibility part that we're talking about. Experimentation is where most of you are excited about. This is where the model development take place. You will be doing your literature survey. You will be looking at the papers that I talked about. You will come up with your own approach. Not one approach, you will come up with multiple approaches so that you can compare against each other, which one of them is working out. And the last two stages are about deploying the solution, facing the real traffic, facing the real test. Okay. And it's good to have at every stage an artifact, right? A documentation of that, what happened in that stage. So that you know, so when you start with the problem formulation, you have the right problem, you have an agreement with your business team, with your product team, right, with your engineering team, that this is the problem, this is the scope of the problem that we are working on. Okay. And data inventory, that these are the data sources that we would need in place. If it is not there, we will need them. If it is there, well and good, they have to be quality data. Sometimes you will see when you're working industry, people are ingesting data into the data lakes, data warehouses, into a data store, right? But they're not monitoring the quality. And you would have heard this adage many a times, garbage in, garbage out, right? You feed garbage to your model, you will get a garbage out of it. Right? So this is very critical. These are the early stages, and if you do your things right in the early phases of model development, it will serve you good. You won't face too many surprises, hopefully, when you're deploying the models, or rather actually when you're developing your models. Yeah. Phase one, read through it. We are talking about that. What is the motivation? What is the business problem, right? Why do you need a DS solution in the first place? Maybe a simple heuristical or a statistical solution would suffice, but there could be cases when ML model is already existing in the system, and now you have to improve upon it, right? You figure out, like I said a couple of seconds before, you figure out what is the acceptance criteria, what is the success rate. If someone is asking you to improve the clickability of results on your page, I'm showing you search results. The results are relevant. Okay? If I have to improve, then what are they expecting? Are they expecting 10%, 5%? What is good enough, right, for me to pass them? So you define a couple of metrics. What is the business success criteria? And then in your in your formulation, you define what is the DS corresponding DS metric. Remember, I just talked about DCG, NDCG, ROC AUC, right? ROC AUC. And similarly, you have PR AUC also, precision recall, area under the precision recall curve. So you define your DS metrics also, model metrics. Okay? And by experience, after doing a couple of iterations, you will figure out the relation between, if you move your DS metric by a certain amount, the business metrics move by, let's say, if you move your DS metrics by X, there is a corresponding Y percentage movement in the business metric. Over a period of time, you will have to build that insight so that you know that anything that you're developing offline, right? I mean, any model that you're developing, it translates into the business problem that you're solving, right? It is actually solving for it. WMAP, don't worry about it. It's called weighted mean absolute prediction error. So prediction error is fine. I mean, what was the actual value and what was the predicted value, the difference. Absolute is so that you are not worried about the direction, right? And mean is mean. Weighted is that certain instances will be given more weight. DOH in Flipkart term in forecasting, it stands for days on hand. A product that you buy, right, on Flipkart website, it is stored in the inventory. Okay, so how long does it stay in the inventory? That is something which we call DOH. So it's an important metric here when you're developing a forecasting solution using time series or any of your classical models. Right? Then how is your WMAP corresponding to DOH? You have to understand that, but this is part of when you're formulating the problem. Sometimes you will not have it in the first go. So when you're starting with a heuristic solution, you may not have this relationship established. It will come with practice. And then few things that, do you have the right engineering solutions in place? If not, then correspondingly or in parallel, even that system has to be put in place. Okay, I just talked about it. It's about requirement gathering, and there are metrics that we are talking about. Now, if you can optimize directly for the business objective, well and good, but sometimes you will not be able. So let's take some examples. A lot of companies, Google, is a ad mammoth, right? I mean, Google gets its revenue majorly from the ads. Right? So one of the problems over there, or on the search page, you will see when you're searching for anything, right? You will see first few results are ads, right? So business tells us they come, and the business model that is there is that you pay. When I say you, an advertiser will pay to Google, okay, only when there is a click on the ad, only when users are interacting with it. Okay. So that's their business model. They have told advertisers that we are not going to charge you indiscriminately. Okay. Only when there is a performance, only when people are interacting, and we are giving you the platform. Okay. Only then we'll charge you. Okay, this is so the problem that now business team comes to you is that increase the clickability, right, on my search results, which means show the ads to the users, which will have more clicks. More clicks would mean more engagement for the user. User is not dissatisfied. At the same time, the advertisers whose goal in the first place was to get the users to their websites, that is satisfied, and the platform, that is Google ad system, that makes revenue, right? So the problem that was a business problem, get me more ads or clickable ads, show more clickable ads, right? Now, how does it translate into your business in your data science problem? It is that of click prediction. That if I show an ad, a result, will it get clicks or not? Right? As simple as that. Now, so you go and talk to the business team. But if it's the first time you are building a solution, okay, there are other things in the ads world, and if you are familiar with the literature, then you will know that the moment you make a search request on the search engine, different advertisers will be competing to get your attention and to show their ads to the user. Okay. At that point in time, an auction is run. Now, the auctions are of different natures. Okay. There could be that you pay a fixed price when a click happens on your ad. Okay. Or there could be other kind of auctions. There are VCG, which is weekly clock growth auction. There is GCP, generalized second price auction. So you ask the business. We are still in the phase of business formulation. You ask the business, do we need auctioning at this point in time? Right? Maybe not. In the first version, you don't. You keep your solution. You keep your problem simple, right? One moving part at a time. Okay? So you simply focus on CTR prediction maybe in the first group. Another example is that of search results. Are you interested in showing relevant results? Okay. Yes, of course you are, and that's the first version. But are you also interested in the first go itself? If you're solving the problem for the first time, are you also interested in showing diverse content? Maybe, maybe not. In the first version, maybe it will bring in another moving part. It will bring in another complexity to your solution, right? So maybe you want to hold on to it for later. Okay? And then all these things translate into your solution, right? What kind of solutions will you be building it? Maybe in the first go, you will simply do text match. Given a query, given the document, what are the terms which are common in both of them, and you will show those results. And over a period of time, once you have that in place, your system will develop, and then your infrastructure would be ready. Next time you can come up with deep learning models. You already know that there is a matching engine and everything is in place. You can replace your text matching with neural matching. And if you don't have the right metrics, right problem, then you figure out proxies. So one of the examples that I'm giving here is that product comes and business team comes and tells me, okay, show me the results which are of good quality and which will convert more. Convert as in people will purchase more. So purchasability is fine, absolutely. I mean, you understand. So you will say, I will build a purchase prediction model here. And you go back to your desk and you're fine. But then the product comes and tells me, no, I asked you to show better quality results. And then you go back and ask, what is the definition of quality? What do you mean by quality? Right? If you're on an e-commerce site, so quality could mean products which have historically low return rates, products which have, for example, good ratings and reviews. Right? It translates into that. So this is a conversation that you will be having with the business and the product. Okay. But it also entails another problem now. If you look at it, ratings and reviews, there are millions of products we have in our catalog, right? Not all of them have been bought, and they would have bought at different frequencies. Some products will be bought more than the others, right? So it will have this skew, the Pareto distribution that you will see. It's very prevalent and very common in the industry. There'll be sparseness, there will be skewness, right? So you have to have this conversation. Maybe the product team, the business team will go back and say that, okay, no, okay, let's focus on quality a bit later. You focus right now only on the convertibility. Yeah. So baseline, I said when you're building V0, even in V0s of your models, you need to have baselines. Can you compare your solution with something else? An example, let's say I want to figure out as a user, right? What kind of, at what price points would you buy products? This is one of the important problems that we want to solve, right? When user one is coming, maybe the user one is coming from tier 1 or tier or metro regions of India, right? I'm making certain assumptions, but at an aggregate level, these are somewhat correct from the data. In metro and tier 1 cities, people have more spending power, right? So maybe the purchase power, the price points at which they will purchase, that will be higher. Of course, it reflects to the quality of the product also. But in villages, in tier 3 cities, the price points at which user will purchase will be slightly lower. So this is a problem that I want to solve. Okay, what is the affinity of a user towards different price points? Okay? This is the business problem. Okay? And you have to solve for it. My data scientist comes and tells me, you know what, I'm going to use temporal point processes. Now, fair enough. I want to use neural networks. Don't worry about temporal point processes. As the name says, temporal is on the time axis, points on the time axis. So effectively, you are trying to figure out that when will an event happen, at what probability, and all those things. You can model even price affinities by that, which is saying that if you had previous purchase points on the time axis, right, can you predict the next point? And there are different ways. So don't worry about it. But my point is, I can come up with, my data scientist has been reading a lot on the temporal point processes. So say, it's just that I've got this hammer. Show me the nail, and the nail here is this particular problem. And he wants to solve, or he or she wants to basically apply temporal point processes. Fair enough. The other person says they're another data scientist. He or she says that neural networks are the flavor, current flavor. So I want to use neural networks. Fair enough. So you want to develop it, right? But you start with a very simple solution is what we are talking about. And here also, do you have a baseline to beat? If I developed temporal point processes solution, a neural network solution, right? How good is it? I have to compare it against something else. Right? So you build your baselines, and maybe the baseline could be a user who has done these activities in the past. You simply figure out what is the most frequent price point at which the user has bought, and that's your baseline. You say that if I use this simple statistical baseline, this is a good enough prediction, and I want to beat that. So you need to have a baseline. Same goes for recommender systems. You don't start with your neural recommendations or deep neural recommendations. You start by showing popular content, and then to the user, if you have enough history about the user, what has been popularly browsed by that user. So you can have personalized popular recommendations. I'll skip this one. The next is the data readiness. You need to, like I said, that you need to talk about with the business team that what is the data that you will need to develop your solution? What is the data that is available? What is the bare minimum data that is available, and what is all data that you need? I mean, more the signals that you will use, better for you in general. But do you have all the signals, and do you want to start with simpler signals in the first place, which are easy to compute, right? And then what is the quality of that data? Sometimes, like I said, in the systems, people are just ingesting their data. There could be a order team which is processing the order data. There could be a search team which is showing the search results. There is a recommendation team which is showing recommendations, right? All these teams are pumping their data into a data warehouse, a data lake. Okay. Now, what is the quality of the data? Are they consuming it, right? Otherwise, you will have a lot of data quality issues. And the moment you start developing your model, you will find the data is not good enough. Okay. You talk about that. Sometimes you also have to be also careful about if it has PII data. PII is personally identifiable identity data or information. Okay. So I can't have a user email address in clear text or user phone number in clear text, which I can identify. You would want to hash them. You want to obfuscate them. So all those things have to be there. Privacy breaches should not be there. And at this point in time, this stage primarily deals with data. You have the data. The problem has been given, and you said that no, I want to apply supervised learning. Do you have the labels? You also have to worry about, do you have the labels? And if you don't have the labels, you have proxies for them. Can you create proxies? Sometimes you may not have the right proxies. When we talked about quality, right? No one told you what is quality. So you have to create the labels for the quality, returns, the ratings, reviews, right? In production, you also have to be, so I'll keep on using this problem of CTR prediction. It's a very simple problem, as well as very common problem in the industry. Okay. We'll keep running through it throughout the sessions. When we go into the case studies, we will have multiple ways of solving it at scale and the challenges. So CTR prediction stands for click-through rate. Given a content, how many clicks, how many times did that content got clicked, by how many times it was shown to the user. Okay. So in data inventory, when we're talking about data, so if I'm talking about CTR prediction, clickability, you have to figure out, I showed a content. Did the user click on it? Can you stitch them? Typically, you will be surprised when you will go into industry, right? When you do your internships, you will be surprised that people are just storing aggregate numbers, that how many times a search was made, how many times the ads or the results were shown, and how many times you got the clicks at an aggregate level. So I got a request for red Nike shoe 10 million times in a month, right? Or a million times maybe in a given day, something of that sort. And it got some 10,000 clicks. But what you need is, at the moment when you showed it, right, to the user, and at that moment, was there a click or not? Did the user respond to it or not? And that translates into your CTR prediction problem. That's how you get your labels. Okay. Once you build that model, the next phases will come that, are you getting good clicks? Sometimes there are clickbaity products. There are guys, actually, I'm just using an example. Let's say someone is trying to lose weight. Okay. And you know from the history, yeah, that guy is trying to lose weight. But guess what? That person has right now searched for shoes, right? Can I show a weight loss product over there to the user? I might actually. Advertisers sometimes do that. Okay. And will it get a click? Yes, it will get a click. And that's a long-term intent of the user. Maybe that's a burning intent, but it's not the right intent at that point in time, right? So it's a clickbait, is what I'm trying to say here, right? So you can show clickbaits, but it's not a relevant result. So you have to differentiate between what are good clicks, what are bad clicks. So all this thing comes, maybe, but it's not part of the first problem that you have to worry about. And other things that you have to worry about is, are the features logged for you? Okay. What are the features? Temporal, what time of the day did the person come and visit me? Maybe certain people are visiting during night times. Right? Some people are early birds and they're visiting during morning or during the daytime of during the middle part of the day, right? Which geography are they coming from? So these are the features which will help you a lot when you're developing personalized solutions. So when you build click prediction model, can I predict the probability of a click for one person differently from the other person, right? I may not be clicking as much, but the other person will be clicking too much. So can I personalize it? And if it's a personalized model, then you need to have such features also available. So you talk about that. What are the features that you will need? The other thing which people don't focus too much on is, like I said, at that point in time. What was the user behavior at that point in time? Okay. Let's say after a month, you figured out user interacted with something. You showed a content, you shaped user's behavior, you showed a lot of content to the user, okay, and user clicked on that. Then the system will reinforce that, right? But this information has been made available to you only after a number of days, after a number of events. It's not, you didn't learn it at the first go. When you first met the user, at that point in time, you did not know about users' behavior or interests. So at that point in time, when you did not have that information, how did the user respond to your results? Right? So you need to have snapshot. And as you're building the history, as user is giving you more data, right? So you log that information at that point in time is what we're trying to say. Okay, so work with snapshots as much as possible. Quality checks we talked about. And then what's the user feedback? Feedback could be in many ways. You're typing in a query, you mistyped it, okay? You didn't get a result, you reformulated it. So that gives you a feedback for your spell corrector. Okay, I have done something, right? You typed query in one particular way. Let's say someone wanted to, someone was searching for glucometers, but they don't know. They know that it's used for testing the sugar levels in your bloodstream. So they simply type sugar testing machine. And sometimes systems will understand and sometimes they won't. This is called vocabulary gap problem in search. That there is a difference in the vocabulary of the searcher and the system, right? So reformulation can help you with that also. If the user reformulated when he or she did not get the result in the first place, they reformulated the query. So do you have these feedbacks also with you? Yeah. So that will always be the case. I mean, snapshot will become historical, but snapshot is at that point in time. What was the user's, what was the user information at that particular point in time? Okay. Historical is aggregated over a period of time. So and that is one information. Okay. That's one part to it. There are other things also. Let's say when I showed a product, okay, what was the quality of that product at that point in time? Was it good? Let's say how many reviews did that product had at that point in time? Okay. Now, if I'm building my solution 10 days later, okay, now on the 10th day, I am building my model. I don't need to see what is the quality of that product on the 10th day. So on the 10th day, I don't want history of these 10 days, but rather I want the snapshot at the point in time when the product was shown. Okay. So on the 10th day, if you start working with the history, right? I showed product on day 0, and now I'm building my model on day 10, right? I have got enough information about it. Now, if I'm building this, if I'm using this 10 days of data, and I'm predicting for day 0, I'm already looking in future when I'm using day 0 data. You get the point, right? And this is also one of the problems that's called feature leakage. It leads into feature leakage. Sometimes when you develop your solutions offline, you wonder that, oh, I have got a very great solution. It's going to kick it in production. But the moment you launch in production, it falls flat because you have already looked in the future when you were developing future. And so snapshots are very, very critical to handle those kind of situations. I gave you an example of the vocabulary gap, right? So like I said, it's always data before science. These are some of the hard yards that you have to do before you develop your models. The other thing is measure also. So like I said, when you have to evaluate your models, you have to look into more than one metric. I think Rishabh also talked about it, right? When Rishabh was talking about recommender systems, he's also saying that he also impressed upon you guys that you need more than one metric. Example, add CTR prediction, the raw KUC that I talked about. Now, if you look at it's a classifier. I mean, if the classifier was class 1 versus class 2. I solved my problem of click prediction into two classes, clicks or no clicks, right? Now, there are multiple ways of evaluating that. Either you can have all your training points, all your data points. Let's say I had 1 million requests from the user and I showed 10 results to each one of them. So it resulted into 10 million points. User gave me a feedback, click or no click, right? I get them. I have now that data set with me. I got their feedback. I can measure the AUC of that entire data set. But this is across the entire data set. It is not for that particular request. You got the point? User had one request. I showed 10 results. I want to see on those 10 results how well I did. So I need to have certain metrics for that also. While the AUC would be for the entire data sets, all things aggregated. Okay. Then there are other things about, so you start coming up with multiple metrics. One was the classifier metric of ROC AUCs or PR AUCs. Then there could be the ranking metrics, MRR, which stands for mean reciprocal rank. When I showed 10 results, at which rank was the relevant product shown to the user or clicked product was shown, right? So you measure the reciprocal of that and you average it across all the requests. So that's a ranking metric. And you come up with such many metrics so that when you are evaluating your model, you are looking at them. ROC AUC sometimes, because of the imbalance in the data, you will find that click-through rates are very sparse. 1 out of 100, 2 out of 100 products will be clicked. Okay? It results into imbalance in your data set. That the positive classes are very highly dominated by the negative classes, right? So ROC AUC kind of metrics can lull you into a false sense of security, because the false positive rate that we talked about, right? Even if I move my false positive rates in thousands, tens of thousands, the rate metric, the false positives will move by such absolute volume, but rate metric, FPR, will not budge too much. Okay. What happens because of that in the ROC AUC curve that you saw? Your TPRs, true positive rates, can shoot up very, very quickly, and it will give you, okay, even though the false positives haven't moved in the rate terms, right? You get, okay, your ROC AUC curve, the AUC under the ROC curve has shot up, okay? And then you start wondering where I'm going wrong when you launch that model into production. Maybe your false positives are dominating. So you start looking into partial ROC AUCs, that smaller FPRs, false positive rates. So you need to come up with multiple metrics. And then once you have got first set of metrics, then you talk about other metrics that are important, that will be important for your solution. For example, the CTR again, right? I talked about good clicks, bad clicks. Once you click on it, how quickly are the users coming back to the page? What they're interested in that? So what is the quick back rate? So now how many of you are aware of multi-objective optimization? Okay. So can I optimize for two objectives simultaneously is the problem here. I mean, as the name suggests, right? CTR, click prediction, is one objective, but can I simultaneously reduce my quick back rates? How quickly the user is coming back. Okay. There are many things to worry about it, but in a very simplest term, can I formulate it as maximize my PCTR, probability of click, plus lambda times 1 minus quick back rate, right? Maximize that. So it becomes a multi-objective problem. And so you need to be aware of that. But if you need to have quick back rate in your formulation, do you have the data for that? Is it instrumented? So I'm mixing all the business problems together. Like I said, feasibility, data inventory, and DS formulations, all of these are part of one group of phases. Feasibility now is the problem that you are asked to solve. Is it feasible to solve it right now? I mean, do you have all things in place? Is what we are talking about. Okay. Does there exist a solution? Maybe sometimes, as you would have seen in computer science, maybe the problem is NP hard. Then do you have an approximate problem for it, or approximate solution, which can be solved in reasonable amount of time with reasonable accuracy? You don't need the perfect solution. So you worry about the feasibility here. Okay. Maybe you have built a very good solution. Now, How many of you have heard about these pre-trained models, GPT, GPT-3, Transformer, BERT? A decent lot, right? So these are big models, right? These have, many of them have billions of parameters. So when you're serving, will it be able to fit in memory? You've already developed some programs, right? When you're running your program, at that point in time, is the memory of your computer, right, at that particular machine right now, which is serving the traffic, is it sufficient, right? So that will be one of the constraints, right? The other thing would be, okay, you have a big model and it's a very deep model, right? Many layers in it. Let's say I deploy it in my search system at Flipkart, right? You fired a query and I used T5 or a BERT model over there. Okay. Guess what? If I am getting my results, and my latency concerns there are that given a query, I have to show you results in 200 milliseconds, 300 milliseconds, in sub-seconds, right? The order is that. But if this model is taking 4 seconds, 5 seconds, then it's not a scalable solution. You've got a very great solution which you built, but it's impractical, right? So you have to worry about that. So when you do the feasibility analysis, you also look at the quality of the data, that you don't have garbage data with you, right? So some of the data cleansing and data quality checks have to be put in place. Like I said, is the data censored? Sometimes, what is an example of a censored data? Let's say you want to figure out the life expectancy of a drug, and what's the effect of a drug on life expectancy. Some people participated in that trial when you did the drug trial, okay? But let's say they turned 70 and after 70 they stopped taking the drug, okay? Now, do you know the effect of that? You don't know that. I mean, the data after 70 years is not available to you. So that's sensor data. So do you have sensor data with you, right? Do you have personally identifiable data with you, right? And if you have, then, and if your concerns are privacy concerns, that you don't want to bias your models, you would have heard about bias in the models, ethical ML, fair AI, right? All those things. Those things are one thing, and then PII data is another thing. Do you have that? And if you have PII data, can you obfuscate that? And if the data is very, very sparse, then subsequently the solution space also changes. And maybe at this point in time with sparse data, you can't build a solution. So you visualize them, you plot the distributions of the features, you plot the distributions of your labels, okay, of the target variables. You figure out the imbalance. Like I said, in CTR problem, it's a highly imbalanced problem. You just get 1 or 2 clicks out of 100 impressions. And when you have data at millions of level, this problem magnifies, right? When you have millions of records, then you will have your positive classes only in thousands. So your solution space will change. Now, can you solve it, right? I mean, is it feasible to solve? Do you have the right data instrumentation and everything? So you do that. Okay. So I talked about labels, right? You got the business problem. Now you're thinking that, do you have the labels? If you don't have labels, can you figure out proxy labels? I mean, you don't give up on the problem, but you figure out, do you have the labels? Sometimes you do have labels, but they're noisy labels. Okay. Let's say I wanted to figure out the relevance of a search result to a query. The way typically it happens in the world is that you given a query and a set of results, you send that result to a human labeler, okay, or a set of human judges. They will tell the results that you showed were relevant or not. That's a very pristine, high quality data. Right? Maybe that's the requirement that your model has. Okay? You say that until you give me that, I won't get started. I won't build my solution. But then there are proxies to it. When you showed the results to the user, users also gave you feedbacks. They were noisy. Like I said, there could be clickbaits, but user also gave you feedback. Can you use that? So now you've converted your problem into a supervised problem. When I say it's still a supervised, but you've converted into weakly supervised. The weak supervision comes from the weak labels or the noisy labels that you've got from the users. So that's weak supervision. And then you can go and talk to the product team, business team. Okay, I'll make use of this data, but I'll also need parallelly some human label data. So while that thing happens in parallel, I'll start working on this one. So you've moved from infeasible solution to a feasible space. Yeah. And then you can also change your approaches. You can convert this problem also into, when you have small data set, you can convert it from supervised to semi-supervised. So this is another example of this query reformulation, right? I mean, if the product teams and if the engineering team comes to you and sorry, they're not changing. How long it's been happening? Let me start it. Okay. So this is what I was talking about. So don't worry on this one. We were just talking about if you have the feasible data with you. Okay. So one of the examples of the feasibility was this. If I have to when I gave an example of that glucometer versus diabetes or sugar testing machine, right? If my requirement is to solve the problem, so query reformulation. Okay, let me tell you about this problem. What happens when you search for sugar testing machine? Can I internally figure out that it means glucometer? Okay. So sometimes you will see in such systems uh, um, that you expand the query or you reformulate, rewrite the query. Have you heard of, how many of you are aware of search systems, how search works in practice? Okay, don't worry. So few things that we do in search is this. You are given bunch of query words, a query is given to you. You try to go beyond the words. Okay. So if I had just matched for sugar testing machine, you will see sometimes you might see weird results. Okay, it's still not a solved problem. Okay. This problem, like I said, was a vocabulary gap problem, right? People would search for kasavu saris. People who are aware with kasavu saris, they know it's a Kerala sari, but the seller might have actually put in our system as Kerala sari or set saris. They're different names, right? So that's the vocabulary gap problem. Now, how do we solve for it? We try to reformulate the query. If I know that this is a tough query which hasn't fetched me results or it has got me very few results, right? Then I will try to reformulate, rewrite the query automatically. Sometimes it can also result into further weird results. Okay, I could reformulate it to a totally different query, which is called concept drift or query drift, the intent drift in the query. But don't worry about it. So my problem would be this: given a query, if I'm matching it, can I reformulate it? If it's a tough query, so can I reformulate my diabetes testing strip or sugar testing machine into glucometer and then search on my system? So this is one of the problems that we have to deal with when we have to show the results. You will be surprised that people in India, I mean, coming from different backgrounds, different literacy rates, right? Misspellings are very common. And sometimes the misspellings are phonetic in nature. Sanitizer spelling, you all know the spelling of sanitizer, but people who are typing in sometimes, a person who's English, for whom the English is not the first language, right? They'll be typing in CENITYGER, something of that sort. In terms of edit distance, it will be very, I mean, it's very tough query for you to correct, right? So in real time, I can do a couple of things that I can tell that I did not understand it, or I can try to understand it as to best of my capability, okay? And then show the results. What I'm trying to say here is that you do it implicitly. You show the results by trying to autocorrect it. Sometimes the autocorrection would happen in the wrong way, but we hope that more often than not, we are correcting it in the right way. In the same way, in reformulation, the query reformulation, we hope that more often than not, we are reformulating it in the right way and showing results, the right results to the user. People are typing on Flipkart queries like ground touching dress, which is actually an anarkali dress. Anarkali dress will fetch you the results, but ground touching dress may or may not. Can I understand it? So that's a reformulation. Can I reformulate a tough query, right, into a query which my system will understand? Now the latency would be people, my engineering says that I have to show results in sub-second, right? And there are so many systems. A spell correction will kick into place. I'll also have to figure out the category of the query. Is it, when you said diabetes testing machine, is it actually talking about a machine or is it talking about something else, right? What's the category of that, right? So category of the query. Then I will have to understand many things. I mean, now the point is, this reduces for each component of the solution that you're building in the search path of a query, right? The amount of time that you have to surface your results will be small. And if the engineering team or the product team comes and tells me, okay, we can do query reformulation, but all you've got is 5 milliseconds, right? Now you can't apply your BERT kind of models. You can't apply your deep models, very big models, or even the simple models that you have. It can't take too much time. Okay? So what could be, so either you can go back and say that, okay, no, it's not feasible, right? Or you have a conversation back and forth. Okay, let me do one thing. At least for the queries which are frequent on my system and I don't understand, I can create a mapping, right, offline. When this query comes in the user path, at that point in time, I will look up in the database the corresponding query and I will show it to the user. It's a lookup. Lookup is very fast. When you use hash tables and all those things, the lookups are fast. So the problem is feasible in that sense, but here's the problem, that you can solve only for the queries which you have seen in the past. You can't, and you will be surprised in search that a lot of queries, like this is called a fat tail phenomenon. The tail is very big, and the tail, when I say tail, when you plot the frequency against the query or the number of queries, the number of queries or the queries which appear only once or twice, right? They have a good probability mass. So when you plot it, you will see that a lot of probability mass will be under those queries. Okay? So this long tail phenomenon exists, this sparseness, and like I said, these are called 80-20 Pareto distributions also. So these Pareto distributions are very, very prevalent in industry. Okay? So my point here was that you won't be able to address a lot of your queries by keeping a lookup table. So feasibility now, the conversation that you're having, the problem space that you're trying to solve, that reduces because of this time constraint. Yeah? I can only address in 5 milliseconds, maybe I can address only the queries which I have seen in the past, but a lot of queries will go unaddressed. This is where most of us spend our time. A data scientist typically spends most of his or her time on creating experiments, developing experiments. Okay, you are done with the first 3 phases, right? The first group phase, where you talked about the feasibility, availability of the data, right? You have the labels in place. You agreed upon the metrics, that what's the impact that you want to. You formulated into your DS solution. Okay, so you know that it's a supervised problem. Now you go and try to solve it. Like I said, when you are reading a research paper, when you're writing a research paper, you first research what has happened before. Okay? So at this point in time, you start reading papers, you start doing your literature survey. You figure out what other researchers have been doing in this particular field. Maybe this vocabulary gap problem that I talked about. right? It's a very tough problem to solve. So people have spent a lot of time over there. At this point in time, you will start reading those papers, figuring out those approaches. Sometimes the problems will be in different domains also. At Flipkart, I'm solving for e-commerce domain, but the problem has been solved in web search domain. Web search is where you are just typing any kind of query, right? I mean, it's informational. You want to figure out how to make egg fried rice, right? You will be searching on Google, but you won't be searching it on Flipkart. Hopefully you will do at some point in time and we'll show you the ingredients, but that's a different point, right? But my point is that the nature of queries are different. So some people would have solved this thing differently on web, but then still some ideas are applicable, right? In legal world, in finance world, in medical field, people would have, if they're searching, as long as someone was searching, right? People would have tried to solve this problem in a particular way. So you research, you figure out how this problem has been addressed before. You combine them after reading those papers, you combine and basically form your own view, right? That this is how this particular problem should be tackled in my opinion. This is the solution to this particular problem. Okay. So you distill down your approaches. You create more than one approach. I mean, that's advised, okay? But start with simple approaches. So that's very, very critical when you start building a solution. Start with a very, very simple solution. If it's possible, when you're developing a machine learning model, if possible, start with a linear model. It does a lot of things for you. The engineering team, the infra we talk about something called inferencing at the runtime when we are invoking our model, right, to predict. That is called inferencing. So they can build an inferencing infrastructure very quickly for linear model, because linear model is simple weights and feature values. You simply take a dot product of the two, you simply multiply them and you're done, right? If they have to do that, all they could do is they simply will maintain this weights table, and at runtime when the query comes or the request comes, you will have the feature values. They will simply do a weight lookup, multiply, and you're done, right? So simple linear models are pretty easy. But if you had neural models, nowadays there are libraries, but those libraries have their own pros and cons. Sometimes they will not be able to work when actual traffic hits, right? They will not be able to scale. Okay. So you start with simple model. Like I said, even when you're building your models, this is a stage where you again go into EDA, exploratory data analysis. Now this is deeper at this point in time, right? Some label distribution, the imbalance, to what extent is an imbalance in your data set? How do you tackle imbalance, by the way, in your problems? Any idea? So let's say, I'll give an example. The click-through rate, right? I have to do the click-through prediction. Click-through. I have 2 clicks out of 100 impressions that I show to the user. Okay. And I've accumulated this over a period of time across users. Okay. I have millions of requests at 2% CTR. Okay. Now, if I take that example of that small baby data set of 100, if I'm measuring my accuracy, what happens if I simply say that all of them are not clickable? My accuracy is still 98%, right? Is that a good solution? I mean, now if you build your models, there's a possibility that, just like you said that, your model could also say that. I mean, if it's seeing a record so many times, there's a possibility it will be influenced by that, right? So your solution could be impacted because of that. There are multiple ways. If you have, like I said, if it translated into millions of records, then I could do few other things. I can do, out of these millions negatives, I could subsample them. I could take a small, maybe I can take 2% of those negatives. And now guess what? I have 2% of positives and 2% of negatives, but it comes at a cost. My data set size has reduced. This is undersampling. I could do oversampling. This 2% data set, the positives that I had, I could simply duplicate them. Okay. So I can artificially create a balance. There are more sophisticated methods like smooth, wherein basically you will say that if the positives, if you cluster your positives, right, you can generate synthetic points. So let's say if there are 2 positive points, you draw a line between them, and then you pick your points on those lines. Okay. So you've got some artificial positives also. You can do that also. Instead of undersampling, oversampling will increase your data, right? Undersampling will reduce your data. Okay? When you increase your data, it will have other challenges. Sometimes your systems, your solutions will not be able to scale. You won't be able to hold them in memory. Now, as of now, you will feel that memory is manageable, right? Anything can be loaded in memory, but you'll realize that over a period of time, when you have hundreds of millions of points, holding them in memory and training with them, right, is tough, right? If I'm getting hundreds of millions of requests a day, this is requests, right? And for each request, if I'm showing you hundreds of results, now if I have to train my model, I can't use simple 1 day of data. I have to use n days of data because of this long fat tail phenomenon, and I have to get enough history. So now you see, I've got 100 of millions, right? In a day itself, I've got 10 billion impressions. If I have to do it for 10 days, I've got 100 billions of impressions. I can't hold them in memory, right? So you have to worry about them. Now, coming back to this thing, so this influences your solution space. How do you solve these problems? If there was like I said, label imbalance to begin with, what you could do is, you know that the incidence rate is 2%. Okay. You know about log loss function, right? You've already did that, right? So what you can do is the positive class that you have, you can weigh them highly. You can weigh them more. It is, if you look at your batch gradient, the gradient or the loss that you compute, right? It's yi log pi, right? I mean for the positive part, right? If yi is positive. Now, if I was oversampling it, right? I was simply duplicating these yi's, but in summation, it simply adds up over there, right? It becomes nyi log pi effectively if I was duplicating it n times. So n becomes a weight of actually that particular class. So can I give a weight? So now I can do weighted log loss also. I can assign weights without changing my data. So these are different things that will come handy. But to even go into that solution space, you first have to look at what kind of problems exist in your data, right? Now, so that was on the label, right? Sometimes you will also see, I talked about this Pareto distributions, right? There is a skew, right? When you have a skew, there is a huge variance in the data. Okay? And most of your models, right? They make an assumption that the variance in the data is same. In the sense that if you take one sample versus another sample, if you sample it from tail, if you sample from head, the variance won't be very high. So, but these assumptions are violated in practice many times. So you do transformations of your features. You would hear about Box-Cox transformation. You would hear about square root power transformations. You can take a square root. You could take log of the value, right? When you do these transformations, the variance reduces. Some of these are variance reduction techniques, and sometimes it's needed for the relationship also. Maybe you have a log relationship. If I'm talking about linear regression, maybe the relationship is yi equal to log xi. So I would have to do the transformation. Right? It becomes linear in the log space of the features. So you have to do those kind of analysis. If does that kind of, for a variable, independent variable, does that relationship exist? Okay. Then you figure out you have hundreds of features now available in your data, right? Are all of them equally important? Sometimes features will be correlated to each other. I mean, if I am figuring out in the classical Andrew Ng's course, right? If I'm figuring out the price of the house given an area, if the area is given to me in square inches, square feet, and square meters, I don't need all three of them, right? They're correlated. Or maybe instead of that, someone gave me area and number of bedrooms. Now they're weakly correlated, right? But there's a correlation. There is. So you have to correct for it. We'll talk about it. I don't want to go in there right now, but this is something that you're talking about, right? When you build your logistic regressions, the linear relationship is in terms of log odds. You take the odds ratio, take log of that. Now you have linear regression, right? So log of this probability, the ratio of this probability is W transpose X. You have to correct for it. So when you do the undersampling, so if you look at the denominator in the second equation, That's the sampling rate in a linear model, right? So, and that's a label probability in that sample. So we'll talk about it in the second session in more details, but you can address it. You will have to correct it, but it also depends on the use case. If you were to simple rank by W transpose X, you will figure out that this relationship is simply shifted by log R, this log odds. So and R is a constant because it's a sampling rate. It will be same for all the points, right? So your one point, which was one training record, which had a higher score than the previous one, it will always continue to have that relationship irrespective of this, right? So does your solution require this correction? Maybe, maybe not, right? If you, for example, if you needed true probability, then it needs this correction. But if I simply needed to rank the content, then you don't. Right? So it varies from case to case, but you're right. There is a distributional change, and in many cases, you will have to account for it. So I was talking about some of the EDS that you have to do. You have to figure out the importance of the features, which features are important. And to figure out feature importance, then you will have to apply certain techniques. Filter methods, wrapper methods are there. You figure out what is the importance of a feature to the target variable, right? So you can figure out the correlation between the two, which is, I mean, you can have a linear correlation, but sometimes the feature may not be linearly correlated with your target variable, right? In such cases, you can figure out, you can resort to some other mechanisms. Maybe you can figure out mutual information. How many of you are aware of term called mutual information? Okay, not many, but yeah, it goes into the information theory, right? So you can figure out the mutual information of the variable with respect to the label. Right. So in the experiment phase, like I said, you start with linear models, simpler models. These are very easy to maneuver, very easy to manage to begin with. It puts a lot of systems, a lot of founding blocks in place. Right? These are all common sense, by the way. But sometimes what happens when you're developing models, right? You get so awed and amazed by the complexity of the model or the solution space that you forget about putting basic things in place. Right? So it's nothing more than that. This is an example that I keep on discussing a lot. When you're building your recommendations, right? There was a recent paper in RICSIS conference, Recommender Systems Conference in 2019. And it, by the way, the references that I put in here in the slides, they are not exactly the name of the paper, so the title of the papers, but I made them a bit more palatable, but I have the links here. So it talks about, are we really making progress? Okay. And when they say progress, it means that if you go to conferences nowadays, and the papers that you will find, all of them have neural solutions in them. I mean, more often than not, right? And the authors here, they are talking about, I mean, are these neural solutions really helping you? Okay. Are they really beating the baselines? Okay. So they try to reproduce some of the neural solutions on some domains. And they found that more often than not, your standard, very simple solutions, they are able to beat your neural solutions, or at least they are at par with them. Okay. And the lesson here is that, at least when you're working in industry, when you're really solving for a problem, don't reinvent the wheel or don't start coming up with very complicated solutions. Start with simple baselines. How many of you are aware of collaborative filtering here? So for recommendation, if I have to recommend a product, collaborative filtering says that if somehow I'm able to figure out two items are similar to each other. Now let's say I have to recommend an item X to the user U, right? I'll try to make use of this, and this user has done some activities in the past. Okay. The activities mean the user has interacted with an item set Y. Okay, Y1 to Yn, different items had existed for which I have the user activity. How can I recommend that? User hasn't interacted with this item X, so I don't know user's affinity towards this item? Will the user like it or not? What can I do here? And commonsensical thing is that if you, I mean, it's like in real world, right? If you're friends with a person and you know what that person is like, right? And if that person has friends, right? And if you know your nature of relationship, you can. There's also a possibility that you might be friends with the other person. I mean, this transitive relationship holds over there. Something of that sort happens in collaborative filtering also, right? So you'll try to figure out the similarity of this item X with the item Y's, with which the user has interacted with. Okay. You also figure out the degree of similarity between X and Y. Okay? And then you take a weighted average of that. Okay? And then you'll say and normalize it by the total similarity. Very simple weighted mean, right? And then you will say, okay, this will be the affinity of this item or the chances of this user liking this item. That is as simple as that. That is very heuristical, that is very memory based. You relied on the past data, users past history. When you don't have that, there are multiple other ways. But you start with that, okay? Collaborative filtering. And the baselines will be popular items. Can I show popular items? Things which are selling, they are popular for a reason. Many people are buying them, right? So can I recommend them to the user, to a user to whom I haven't recommended this product before, but others have liked it? Maybe I can use the wisdom of the crowd here, right? So you start with that. So when you're building your solutions, you start simple, you make them manageable. And then you go into slightly more sophisticated solutions. And every time you iterate, you have a previous baseline to beat. And that really tests, I mean, the solutions that you're building, are they really making a difference? Are you able to beat them? This is an example of, so let me do a time check. When do we take a break? 10:30. So shall we take a break now? Sure. Why don't I do one thing actually? Let me finish this experiments, quick examples. We're talking about examples. So I talked about query spell correction also, right? People are typing in different things. So you want to solve for it. Sanitizer, that example that I gave, people are typing in different ways. People are typing gym shoes as GIM, right? Shoes. Maybe there's a brand gym that people are asking for. I don't have it. I'll understand it differently, but hopefully at this point in time, I understand that they're looking for gym shoes, right? So when you're creating your solutions, you have to look at multiple ways of solving. There might be more than one way of solving it. Today, if you try to, how many of you are aware of edit distance? Edit distance is simply what's the number of edits you make from one word to another word. Okay. When we say edits, it's adding, removing, substituting characters in one word, and then you translate it into another word. Okay. For example, if I have shirt to short, there is one edit distance. Okay. But if I have shorts to skirts, then I have to edit basically 2 characters. So edit distance is 2. So these edit distances are very common ways of solving, and this problem has been solved way past and I mean way long back. Right? So the algorithms there are dynamic programming based solutions. Levenstein's edit distance, they exist. Okay? So you can solve using that. But the problem is this: when you get a query, when you get a word, the potential number of candidates against which you will have to compare to correct will be very huge, right? I mean, all the words in your dictionary, you will have to compare this given word to which word this word is closer. The gym shoes that I give an example, right? And then you will find that there will be, if there is a query called shirt, but people have mistyped it as shart, S-H-A-R-T, then skirt could be a 2 distance away replacement. Short could be one of them. Shirt could be another, right? So you will have so many candidates, and that's all right if you can solve it. Okay. But sometimes you will also find that if I give you this query in a context, okay, long sleeve shirt. Okay. So in this case, it's most likely it's not going to be a skirt. It's not going to be a short. In the context of long and sleeve, this is going to be shirt, right? So can I make use of context? Now solving this problem impacts your solution space. So I can solve this problem by looking at individual word, try to figure out the edit distance, and there are faster versions of it. Okay, but then I can also look at the context. Okay? And both of them have their own pros and cons. So sometimes a solution space could entail deploying or employing more than one solution. Okay? So it's a combination of the two. Okay? You also address a word in isolation. You will generate some candidates. You will get a lot of candidates. You prune them, and I will talk about it later. But in industry, typically the way you work is that you start with a very large number of candidates. You reduce it to a smaller set, and so apply one solution there. Okay, then use a very sophisticated algorithm. Okay, and figure out the right candidate. So in the first go, you will focus on recall as many relevant stuff as much as you can. And then in the second phase, you will try to go for precision, be as precise as possible. Okay. So here's the point that you can do both of them. So you will find that maybe you would want to use for spell correction, you want to use neural spell technologies, right? New spell is one of the toolkits that is available. It is formulated as sequence labeling problem. What is sequence labeling? You're given a sequence, so long sleeve shirt. It will look at each token in this particular query, try to label it. But here labeling is formulated as correction. So each word, the label for that is the correct word. That is sequence labeling. So this is a neural solution. Now it has its own pros and cons. It can't handle these compounding when two words are actually supposedly to be together, but user has separated them by a space, or they were supposed to be separated by a space, but user has combined them. Right? Because it is working at token level. It is assigning a correct label for that particular token. It may or may not work. But whole point here is that when you're designing your experiments, sometimes you will have to come up with more than one solution. You will have to, and then you have to combine them. Okay. I think in the interest of time, sometimes you will have to look at more data. Let me quickly rush through it. Okay. Sometimes you will have to look at more data. So this is an example from a real problem at Flipkart, right? When we found that working with it was on forecasting and some other, or RTOs basically. RTO is return to origin. When can you predict the probability of a product being returned by a user? Right? So here we are looking at, if I trained my data on 3 weeks versus 3 months, am I seeing a difference, right, in the observation? Sometimes you will see, like I said, the metrics, right? They can misguide you also. Directionally, they will guide you to the right solution, but they can misguide you also. So you will have to dig deeper. And here we found that even though the raw KUC might have been same, right? Or the prediction errors might have been same, right? But the robustness of a solution when I work with 3 months of data is better. When I say robustness, it means the variance, that my predictions are not all over the place. Okay. I'm very consistent with my predictions. If you have an existing solution, maybe I started with a one size fits all. Okay, this is an example of such solution that I wanted to figure out the return to origin probability, the RTO probability of the items that I'm showing to the user. Right? Will user return it or not? I built one solution for BU, stand for business units. Large means large appliances, fridge, TV, ACs, furniture large, right? And then there are books, there are mobiles, there are apparels. Right? These are different business units. We built one generic solution for them. It worked very well for us, but now you are in the experimentation phase. You figured that, okay, my model is penalizing the large category in a different way. You figured it out during your EDA. Now you're working on the next iteration. So in the previous example, it was the role of data. Now, when I analyzed my model, this is called model error analysis, right? When I analyzed my model, I found that on a particular segment, it wasn't working out very well. Okay, different BUs had different behavior. So now, since I've started with a generic model, I got infrastructure in place. Now, can I start with horses for the courses approach, right? Can I build one solution for each business unit? Maybe yes, and that's what we try to do. Remember, it brings in another complexity. Now you have to maintain 6 models. So if any one of those models go wrong, you will have to spend as much time. So there's a trade-off. Okay, last thing, and then we'll take a break. This is just when you're building your models, ensure that you have a reproducibility in the place, right? You have modularization. I was once collaborating with a PhD student for recommendation systems. Okay. And when we were working on experiments, that guy was extremely fast. Okay. And the things he was doing his PhD, right, in recommender systems. So the domain was known. What he had done was he had modularized his all different approaches. Recommendation system. So you know how you have to evaluate. So you have the set of metrics. So he had a code for metrics, right? The data is going to be more or less similar. Sometimes may or may not be. But he had a modular data pre-processing code. He had that. Then sometimes the data is way, way too big. You need to sample. He had a sampler code, right, which will sample the data. That's one. So then there was a core modeling part. So whenever I was working with him, the only thing that he needed to change most of the time was the modeling piece. Rest, all three of them, data pre-processing, sampling, and evaluation, they were constant. Right? Even when, and he put them on GitHub also. So most of the times, 3 Python files, they were same, exactly same. And that helps. You build that when you're building your solutions. These are some of the best practices, right? Reusability. The other thing that you have to worry about is reproducibility. The model that you ran yesterday, if I run it again today, will it give me the same results? There is a variability. This is predictive models, right? So you ensure that the random seeds that you are using in your data, they are same, right? Because at the end of the day, the computers are pseudo-random. They're not exactly random. So ensure that you are doing that, okay? And a few things we talked about. The test data set has to be pristine. It has to be untampered with. It should not be seen in your training data at all. So these are some of the good practices that you have to be aware of. Otherwise, you could already see in the future, right? And then, yeah, then you've lost the purpose there. Modularization, I talked about. Reproducibility, I talked about, right? So there are few things that you can do, right? And sometimes when you're building, actually, let me talk about checkpoints. Sometimes when you're building models, you make small change to the model, right? Small tweaks. So version them, checkpoint them. The BERT model that I talked about, when the number of iterations that you run for, right? That could be different. And there is also, sometimes you fine tune your model. When we say fine tune, you trained your model on one data set. BERT model is that it was trained on Wikipedia and books corpus, right? Then people use it in e-commerce domain. How do they do it? Transfer learning. How many of you are aware of transfer learning? Right. So books and Wikipedia is a different domain. E-commerce is a different domain, right? So people, what they do is they fine tune their models. They add one more neural layer on top of it. Okay. The weights which have been learned previously, they help in this particular task also. And this task specific layer that you added, that will help you improve your models. Now, why I'm telling you all that is, sometimes even the base models that I trained, right? I could train on my own domain data. So what I could do is, I could checkpoint the model. Okay? I would have the models, weights and everything, which I trained on books, in BERT's case, books and Wikipedia. I will have model version number 1 or checkpoint 1. After that, I fine-tuned it on another data set, e-commerce data set. This is called in-domain adaptation of the model. This is a transfer learning that we're talking about, right? So this is adaptation. I could have checkpoint 2. Checkpoint 3 would be when I add a task specific layer. So now I have adapted my model on e-commerce data. I can do spell correction on top of it. I could do query reformulation on it. I could do semantic matching on it, a lot of things. So for each of these tasks, I can have one of their own layers. Okay? So have a checkpoint for them. So you do the model versioning, you tweak your model. Okay. And the last thing is just freeze the environments. I talked about that reproducibility, right? How many of you have worked with Conda environments? Okay. And how many of you have worked with Python? sklearn, Python everyone has worked on, right? Explore Conda. Okay. Conda is a suite actually which will give you all the libraries in one place, but more importantly, it will also give you some environments. So it gives you virtual environments. You work with them. The set of libraries, sometimes even the version of the libraries could be different from one model to another, right? So you have your environments, you work with the environments. You don't work with try not to work with the raw Python setup. This will help you reproduce the results later. And then next level of it is Dockers. How many of you have heard about Dockers or containers? Okay. How many of you have heard about virtualization or VMs? Great. Docker is a lightweight, put in a very layman's term. Docker is a very lightweight virtualization. These are called containers. So environment was at Python level, the set of libraries. Docker goes one step beyond the containers, the dependencies the system dependencies that you would have, right? Even they can also be basically separated from another on the same machine. So when you're developing your models, and I assume that, I hope that when you guys graduate, try to revisit this slide deck again. You will find that some of the best practices will help you. So Dockerize, try to Dockerize your environments and setups. Work with virtual environments. These are some of the best practices, right? Modularize your code. Okay? The experimentation agility will increase tremendously for you guys. We'll take a logical break here.